Hi, this is Karthik, and welcome to the project presentation of scale-free network analysis using Barabasi-Albert Model. This project has been done as a part of the course WL6935 in Network Science and Applications in EC Department of University of Florida under Professor Dr. Depang Wu. So, before I start, I would like to thank Mr. Wu for all the effort he has put into the course and all the knowledge he has showered to us throughout the semester. Thank you, sir. So let's move on and let's start with the introduction to networks and computer networks in general. Well, a computer network or a data network is a telecommunications network that allows computers to exchange data. In computer networks, network computing devices pass data to each other along data connections. The connections between nodes are established using either cable media or wireless media. The best known computers, of course, computer network, of course, is the internet. Let's look at some network terminology we might be needing through our presentation. Network computer devices that originate, route, and terminate their data are called network nodes. Nodes can include hosts such as servers and personal computers, as well as networking hardware. And two devices are said to be networked when a device is able to exchange information with another device. And the type of networks which we'll be dealing today will be random networks and scale-free networks. Coming to random networks, there has been a lot of interest in social networks in the last few years, and a lot of areas in physics have been deeply studied, and one of them was random networks. In random networks, each node is randomly connected, as the name suggests. They are randomly connected to any previous node, and its evolution is studied. The work of Barabasi and others showed that while the physics of random networks are interesting, it had little or nothing to do with human-made networks such as web, internet, friendship networks, social networks, etc., which all fall into the category of scale-free networks. And maybe the most important feature about random networks is that the degree distribution follows a normal distribution. Coming to scale-free networks, a scale-free network is a network whose degree distribution follows the power law, at least asymptotically. That is, the fraction probability given by P of k of nodes in the network having k connections to other nodes goes for large values of k, as P of k is proportional to k power minus gamma, and many networks are conjectured to be scale-free, including the World Wide Web links, biological network, and social networks, although the scientific community is still discussing these claims as more sophisticated data analysis techniques become available. Let's look at a few characteristics of scale-free networks. And notably, the most important characteristic of scale-free network is the relative commonness of vertices with a degree that greatly exceeds the average value. The highest degree nodes are often called hubs and are thought to serve specific purposes in the networks, although this depends greatly on the domain. The scale-free property strongly correlates with this network's robustness to failure. It turns out that major hubs are closely followed by smaller hubs. Another important characteristic of scale-free networks is the clustering coefficient contribution, which decreases as the node degree increases. This distribution also follows a power law. This implies that the low degree nodes belong to very dense subgraphs, and those subgraphs are connected to each other through hubs. And another point worth mentioning with scale-free networks is though hubs are more data transmission and data spreading is widely widely faster and reliable than a random network, they are also susceptible to attacks from network sources. So hubs, they might there might be a device failure or a hub failure. So these are the things which are supposed to be taken care of when you're working with small scale networks. And this shows an example of how a random and a scale-free network looks like. A random network, as the name suggests, is connected randomly, each node to another in no specific sequence and no preference of order. But in scale-free networks, we see that the dotted nodes are the hubs, and the ones which are not are the normal nodes. So we see a preferential attachment over here. Nodes preferring to attach to some other nodes more than the others. There are many schemes which are involved in scale-free networks. Worth mentioning ones are the Erdos-Renyi model, the Watt-Stoker's model, and the Barabasi-Albert model. So let's look at the Barabasi-Albert scale-free model. The Barabasi-Albert model is an algorithm for generating random scale-free networks using a preferential attachment and growth mechanism. In order to explain the phenomena of rich gets richer, which is prevalent uh, in the complex networks in the real world, Barabasi and Albert have come up with a network model in which the complex networks obeys special power distribution. Sorry. Uh, Distribution. All right. And as we have said earlier, it follows growth and preferential. But what do they mean? So, in general, growth means that the number of nodes in the network keep increasing over time. And the preferential attachment means that the more connected a node is, the more likely it is to receive new links. Nodes with a higher degree have stronger ability to grab links added to the network. Intuitively, the preferential attachment can be understood if we think in terms of social networks connecting people. Let's say a link A to B means a person A knows or is acquainted with person B. Heavily linked nodes represent well-known people with lots of relations. When a newcomer enters the community, she is more likely to become acquainted with one of those more visible people rather than a relative unknown. Let's look at the algorithm. The algorithm is pretty simple, and the network begins with an initially connected network of m naught nodes. New nodes are added to the network one at a time, and each node is connected to m less than or equal to m naught existing nodes with the probability that it's proportional to the number of links the existing nodes already have. Formally, the probability pi that the new node is connected to a node I is given by this, where pi is given by ki by sigma j and kj, where ki is the degree of node I and the sum is made over all pre-existing nodes j. Heavily linked nodes, or so-called hubs, tend to quickly accumulate even more links, while nodes with only a few links are unlikely to be chosen as the destination for a new link. The new nodes have a preference to attach themselves to already heavily linked nodes. And BA models, there are two models in the Barabasi-Albert algorithm, namely Model A and Model B. Model A retains growth but does not include preferential attachment. The probability of a new node connecting to any pre-existing node is equal. The resulting degree distribution in this limit is geometric, indicating that growth alone is not sufficient to produce a scale-free structure. And Model B retains preferential attachment but eliminates growth. The model begins with a fixed number of disconnected nodes and added links, preferentially choosing high degree nodes as link destinations. Though the degree distribution early in the simulation looks scale-free, the distribution is not stable, and it eventually becomes nearly Gaussian as the network nears saturation. So preferential attachment alone is not sufficient to produce a scale-free structure. The failure of models A and B to lead to a scale-free distribution indicates that growth and preferential attachment are needed simultaneously to reproduce the stationary power law distribution observed in the real networks. These are one of the few important properties of Barabasi scale-free networks, being the degree distribution, the average path length, the node degree correlations, and the clustering coefficient. Let's look at the program simulations now. First, I would like to start off by demonstrating how a scale-free network looks like. So we'll do that first. It's asking for, let's generate one with 100 nodes and a degree distribution of 2. So this is what we got. So this figure displays 100 nodes which are connected to each other, and the degree distribution being 2. We might expect that the first node is going to be the hub node, but the evolving capabilities of the nodes is dependent on the preferential attachment algorithm which we have set, which means that the basically which basically means that the first node which has been set doesn't necessarily be the hub or the most important node. There could be other nodes in the structure whose connectivity degree is much more than the initially set up first node. And let's simulate the Barabasi-Albert algorithm. Let me change this. So in the simulation, in the program, we have two important files, two important steps basically. So the first one would be the generation of a network graph. The second one is to add new nodes with a specific preferential attachment. So let's do that. So I'm simulating this structure with only 5 initial nodes, and over time they will grow to a number of 300, and let's see what happens. So as expected, the 300 nodes have been connected in a preferential attachment which has been described, uh, and it forms a geometric pattern as expected. Yes, and this is the graph which shows the degree distribution following a power law. This has to be scaled much more, but yeah, in general, this is the degree distribution which is being followed, uh, which is following a power law. So as we have seen, a scale tree network, the degree distribution of 2 and 100 nodes which are connected. Then we have seen the growth function which forms geometric pattern as the new nodes are being added continuously. And we see that the degree distribution of the Barabasi-Albert model is following the power law or the Pareto distribution as expected. So finally, we have simulated the Barabasi-Albert model, and we have also simulated the growth and the preferential attachment models, and we have proven the degree distribution which has been simulated, it holds good to the power law, which is also as per the assumptions we made. Thank you.